Okay, welcome to our main video on radioactivity in terms of some of the equations. We're going to be considering more the concept of half-life and activity and the equations that lead from this. So to start off straight away, if we considered a dice atom and a coin atom, and we thought about what is the decay constant or the chance of these decaying. It sounds a bit strange, but I'm hoping you'll be able to get that the dice atom, if we said 1 means decay, then the chances of throwing a 1 are 1 in 6. With a coin atom, if we said head means decay, then the chance of throwing a head are 1 in 2. So we'd have this idea that the decay constant is the chance that something is going to decay. That's exactly what it is. It's the probability that an individual nucleus will decay within a unit of time. Now, our problem with the dice and the coin is that we didn't just sit and look at the dice or sit and look at the coin and waited for it to decay. We had to throw it. And that's totally different to the idea of radioactive decay or nuclear decay. Obviously, this is going to happen in terms of time. So the longer that you wait, there's a greater chance that the particular nucleus is going to decay. So our coin and our dice atom does break down a little bit, but it does help us to understand a little bit. In terms of our units for this, we're going to have the decay constant as being measured in chance per unit time. Now this could be seconds, so the chance per second, or it might have to be years or minutes or even months or anything. It's any unit of time. We're going to say that the decay constant is the chance in that particular unit of time that the nucleus would decay. It's got a symbol of lambda, obviously met before, and it's constant for a particular isotope. But be careful, the dice coin analogy doesn't really help. Well, it does help, but it doesn't really tell us the whole story, because you're going to expect, from looking at the dice and the coin, you're going to expect that the decay constant are always going to be less than 1, because that's what you're used to with probabilities. Now, decay constants can be more than 1, a lot more than 1, we'll find out. For example, some decay constants might be 2.9 times 10 to the 5 per second. So that means the chance of it decaying is 2.9 times 10 to the 5 in 1 second. Now you might be thinking, well, hang on, does that mean it's going to decay 2.9 times 10 to the 5 times in 1 second? No, it doesn't. It means that if it could decay, it would decay a lot of times in a second, but obviously it can only decay once. In order to get this number down to less than 1 to make you feel sort of a bit happier, we'd have to reduce the time to microseconds, and then it would be 0.29 per microsecond, which is then, we would say, if we waited for a microsecond, there is a 0.29 chance that it's going to decay. But remember, with time, we can change the amount of time to make our decay constants more meaningful. All right, so don't be put off if we're dealing with decay constants that are more than 1. Next up, we've got the idea of half-life. When a radioactive nucleus emits alpha or beta particle, it changes into a different element. So therefore, the number and mass of the initial nuclei decreases. It does this exponentially. The number drops by a constant factor in equal time periods. How do I know that? Well, we've just said it. This is the decay constant. So in a particular time period, the decay constant tells us the probability or the rate that it's going to reduce by, effectively. So this is an exponential decay. So the half-life, T-half, is the time it takes for half of the radioactive nuclei to decay. That's the definition that you've probably had going around since year 10. And it's totally random, so it's impossible to predict when an individual nuclei will decay, but if you've got a lot of them, you can start to make fairly tight predictions. And remember, a small sample of radioactive material might contain 10 to the 20 nuclei, so it would be very easy, just in the same way that if you threw 1,000,000 dice, then you would expect 1/6 of 1,000,000 of those to be sixes. So the more numbers you've got, the more likely or the better you can predict in terms of how many will decay. This leads us nicely to the idea of activity. Activity is sort of a rate of change, and this is going to be a decrease in the number of nuclei in an isotope. So it's the number that decay. The activity will be the number that decay in a particular unit of time. Normally we talk in becquerels, and becquerels is one decay or one disintegration per second, but again you can have this as disintegrations per minute or per hour or per year, depends on the question. And since each decay produces radiation, this will tell you the number of ionizing particles emitted in a unit time as well. So a decay of 1 becquerel will mean that there is one emission of ionizing radiation or an ionizing particle per second. What does activity depend on? Well, it's got to depend on the decay constant, because the decay constant was the probability of decay. So the higher the decay constant, the more that will decay. But what else? Well, we need an idea here of the number of undecayed nuclei there are available to actually decay. So this is the number of nuclei in the sample. And we've got a letter N, or big N, for this. So again, at the start of this screen, we said this is some kind of rate of change. So mathematically, delta n over delta t, or the rate of change of n, is going to be equal to lambda, which is the decay constant, multiplied by big N, which is the number of undecayed in the sample. And my minus sign here is showing us that it's going to be a decrease. So delta n over delta t is going to be equal to minus lambda n. That's on the formula sheet, and also this is on the formula sheet, which is really the same formula. We've replaced delta n over delta t with big A for activity, and we've lost the negative sign because this is now an activity rather than a decrease, and we're just going to say that activity is equal to lambda n. Okay, take a break. Well, sort of. Let's just make sure you're happy with this. Iodine 135, decay constant of 2.9 times 10 to the 5, half-life of 6.7 hours. Copper 64, decay constant of 1.5 times 10 to the 5, approximately half, and a half-life of 12.8, approximately double. You can see hopefully where I'm going with these numbers. How much more likely is it that an iodine nucleus will decay over copper? Well, it's about twice, isn't it? Because iodine's got a decay constant of 2.9, copper 64 has got 1.5. So 2.9 is approximately double 1.5. They're both to 10 to the 5. So it's about twice as more likely to decay. And how does this relate to the half-life? Well, look, if this is twice as more likely to decay, if the iodine is twice as more likely to decay, then its half-life is about half of this, because if you wait a particular amount of time, you're going to have more decay with iodine, so therefore the half-life will be lower. So twice the decay constant means about half the half-life. So you can see that our half-life is totally linked in with the decay constant. If you had two samples of each isotope that contain the same number of atoms, which one would be the most active? Hopefully you've got this in your head now, that iodine will be the most active. So they're the most dangerous, if you want to say that, because it's going to be emitting sort of twice the irradiation. It's about twice as active. Okay, using what we've got so far in terms of activity, can we now predict how many nuclei remain? So knowing that this is an exponential decay, the equation for predicting how many nuclei remain after time t, when the decay at a constant rate, is this. This is on the specification you're given it, and it's a standard decay equation, an exponential decay equation. So n is the number that you've got left, is equal to the number of nuclei you've got left, is equal to the original number of nuclei multiplied by e to the minus lambda t. So because this is a minus, this is going to reduce e to the minus, lambda being the decay constant, t being the time elapsed. Okay, so using this formula we could do a little graphical exercise here. If we drew a table and plotted a graph of n against t for the first 20 seconds, so we're going to set n is equal to n0 of 10,000 and e to the minus lambda, and the decay constant is 0.1, and t we're going to put in like 1 second, 2 second, 3 second. If good revision to do this. If you do that, you end up with these numbers. So using the formula, you end up with, if you put in T as 1 and the decay constant as 0.1, you get 9,048 left, and then 8,187. Okay, so I'm just using that formula, and you end up with this graph. And it's a perfect graph, isn't it? Because we've produced this graph from an equation rather than this. This isn't a real life decay. We're messing around with the maths to prove this. Okay, so what is the half-life of this graph? Right back to year 10 for half-life, you'd say, okay, well, I've started off with 10,000. I've come down to 5,000 remaining. So if I read across, I'm somewhere here. So, you know, it's not the best graph, is it? But I'm in between 6 and 8, so I'm going to say approximately 7. So the half-life of this graph is approximately 7. But in a second, we're going to try and do this a little bit more mathematically. Now, rather than drawing the graph you've just seen, it would be better to draw a log graph, a natural log graph of the decay, to try and get a straight line. So again, using our formula, our standard exponential decay formula, so the number of atoms left is equal to the original, or the starting number of atoms, multiplied by E to the minus lambda, the decay constant, and T, the time the quantity has been decaying for, or the elapsed time. So let's just take some logs of both sides. So natural log of n is equal to minus lambda t plus natural log of NO. In terms of how did we get this, if you take natural logs of both sides, so natural log of n would be equal to natural log of all of this. We can then use our log laws and get rid of the exponent, get rid of e, the exponential number, and to come up with this formula, which is in the format of y equals mx plus c. Using this, if we plot an activity on the x-axis, so log of the activity, natural log of the activity on the y-axis, sorry, and time on the x-axis, we should get a straight line, and our y equals m minus lambda should be the gradient, and our intercept should be the natural log of the original amount. Okay, so if we do that, we'll have something that looks like this. Again, it's perfect because we've been using the mathematical data, and I have plotted log, natural log of n here on the y-axis, and I've plotted t on the x-axis here. So our gradient should be minus lambda, so our gradient here is 0.1, and that's what we started off with, and our intercept, natural log of NO. Our intercept should equal natural log of NO. So if we do e to the intercept, so e to the 9.21 should give us a number which is our starting amount, and you can see I've done the maths here. Our half-life should be, I'm going to prove why this is in a second, the half-life should be log 2 divided by 0.1, log 2 over lambda, and that's about 6.93. And if you remember, it was approximately 7 on the previous graph we looked at, on the normal exponential graph, and the original number of atoms should be e to the 9.21, so e to the 9.21, and that comes, according to my calculator, about 9997, which is about 10,000. All right, so just to kind of think how we got to this, let's just go back a bit. If you apply natural logs to this equation, natural log of both sides, do some maths and rearrange it, you end up with this expression. This is in the form of y equals mx plus c, and we've plotted log n against t. We've got a straight line, and we've gone back and retrieved our original count, our half-life from the data. Okay, so how can we, on the previous screen I used something that when I said t to the half, I calculate it using log 2 and the decay constant. Let's just try and work out where we did this. This is an important skill to be able to demonstrate for the exam. So using our exponential decay equation, n equals n original e to the minus lambda t. At the half-life, so that if we actually think about at the half-life, let's put some numbers in which mean what we would have at the half-life. So at the half-life, the number we've got left is the original divided by 2, and that's going to equal to NO e to the minus lambda t half, and this is the time elapsed. I'm calling t, big T, half. So at the half-life, we've got half left. Now let's just do some cancelling and some logs, etc. So NO is going to cancel, which leaves me half is equal to e to the minus lambda t to the half. Let's take logs of both sides. So log of a half is equal to log e to the minus lambda t of a half. Let's do log a half equals minus lambda t to the half, and in terms of that natural log of e, if I just use my log laws, I'm just moving this down in front of the log, yeah, and then I've just got natural log of e will sort of just go to 1. So by moving that in front there, just moving that down using our log laws, I've just got rid of the log e. So I've got log half, natural log half is equal to minus lambda t to the half. Moving the minus sign over, minus natural log half equals lambda t to the half. If you know your maths, or if you don't, you can shove in your calculator and prove it. Minus log to the half is the same as saying log 2, natural log 2. And so I've got log natural log 2 equals lambda t to the half. And again, if I just rearrange that, move my lambda over this side, so divide both sides by lambda, I end up with t half is equal to log 2 over lambda. That's on your data sheet. It's important for you to be able to use that. And it is really important in a second, because we are going to just consider how do we know half-lives. But before that, let's just look at other versions of the equation. We might have n. We might have, if we replace n with lambda n, and then we know that lambda n is actually activity. So we can end up with another version of this equation, if you like, where we've got the n equals no e to the minus lambda t, or we've got activity is the original activity e to the minus lambda t. We've also got count rate c is proportional to activity, so we could have c equals c original e to the minus lambda t. Power output of the source. The power output of a source, when these things are used for powering, you can power satellites and things, that's also proportional to the activity, so we can say that p equals p original e to the minus lambda t. Alright, so they all have the general form of this, the general exponential decay equation. So the ones on the data sheet is n, but I'm sure you can see how we can quickly use activity, count rate, and also power. Really quick questions. A radioactive material contains 1.2 times 10 to the 20 atoms, decay constants 3.6 times 10 to the minus 3. Calculate the number of atoms remaining after 1,000 seconds and the activity of the sample after 1,000 seconds. So the first part, using our exponential decay equation, let's put our numbers in. There's the original count rate, e to the minus lambda, there's our lambda, 3.6, elapsed time is 1,000. We get an answer of 3.3 times 10 to the 18. So that's the number of atoms remaining is 3.3 times 10 to the 18. Then we can do our activity. After 1,000 seconds would be A equals lambda n. So 3.6 times 10 to the minus 3 times 3.3 times 10 to the 18, that's the value we've just calculated, so lambda times n. We've got an activity of 1.2 times 10 to the 16 per second, which is becquerels. Another example, number 2, a radioactive sample has an initial activity of 40 kilobecquerels. After 48 hours, this has decreased to 32 kilobecquerels. What's the decay constant? I'm going to use my exponential decay equation. Excuse me. A equals A original, e to the minus lambda t. Let's put in some numbers. 32,000 equals 40,000 e to the minus lambda t. So because I want to be in seconds, I've converted my 48 hours into seconds here. 48 times 60 times 60. These two are both in kilobecquerels, so that's fine. These two need to be in the same. The A and the A original need to be in the same units. And also lambda, because we've got all this in seconds, our lambda is going to come out in seconds. You don't have to convert to seconds. If I didn't, my lambda, my decay constant, would come out in hours, but I've just converted it all to seconds just for neatness, really. Okay, doing some maths. 32,000 over 40,000 equals e to the minus lambda t. So then I've kind of missed a few steps out here. So if I take logs of both sides, then when I do log, natural log of e, I can move the minus lambda and 172,800 down in front of the e, and then the natural log of e just cancels to 1, if you like. So then I've just got a simple expression to solving all that. I end up with minus 0.22 equals minus lambda 172,800, and then just cancelling the minus signs and working out what lambda is, I get 1.3 times 10 to the minus 6 per second. So that's our chance of decay. And finally, hang on, how do we know half-lives? If half-lives can be measured in seconds, minutes, hours or days, it's reasonable to see how you could work it out. So you could sit and watch a source and take some readings over, I don't know, 10 seconds, 10 minutes, 10 hours, 10 days, and you might be able to plot a graph and then work out what the half-life is. But what about the long ones? What if you've got a half-life of hundreds of thousands of years, if not millions or billions of years? You obviously can't sit there in a lab for that amount of time making a note of the decays. It just would not change. If your decay constant is measured in tens of thousands of years, you could watch it for a year and it wouldn't significantly change. So how are we going to do it? Let's first use the decay constant equation to get an activity equal to lambda n. So if we got in the lab 0.01 grams of uranium and it's got an activity of 120 becquerels. So how many atoms are there in 0.01 grams? Well, let's just use Avogadro's number, 0.01 over 238. This is the fraction of a mole. So this fraction of a mole, 0.01 grams of a mole, has got an activity. Sorry, it's got a number of atoms of 2.53 times 10 to the 19. So that's how many atoms I've got in my 0.01 grams. Now I can use the lambda equals A over N by just rearranging this. So I've got 120 becquerels divided by 2.53 times 10 to the 19 gives me a lambda of 4.74 times 10 to the minus 18 per second. So remember, this is a really, really small number because this is uranium we're dealing with, and it's going to have a long half-life, so it's going to have a very, very low decay constant. Now we've got that, we can use the half-life equation, that lambda equals log 2 over t half. I've just rearranged it. So let's say t half equals log 2 over lambda. So log 2, natural log of 2, divided by 4.74 times 10 to the minus 18 that we've just worked out, and we get the half-life to be 1.46 times 10 to the 17 seconds, just to make this number a little bit more reasonable, I suppose, or so you can understand it. That's 4.64 times 10 to the 9 years. So we are now in billions of years, and the half-life of uranium is actually about 4.5 billion years. Okay, so you can see how we can get half-lives not from measuring sources in a lab in terms of their decay. We get them by using the equations that we've been using for the last couple of lessons.